Hey guys, I got a video on the intro to acids and bases, so we're going to talk about acid-base theory and strong acid-base calculations, and we'll also throw in some relative strengths of acids just by looking at their formulas. So let's start off with some acid-base theory, defining what is an acid, what is a base. There are three kind of main areas of thinking for acids and base: Arrhenius, Bronsted-Lowry, and Lewis. I'm going to highlight some of them briefly, but I think you'll find in this unit that we focus mostly on the Arrhenius definition, and then sometimes we look at Bronsted-Lowry a little bit. It just honestly kind of depends on what the type of problem is, the way we want to think or approach it. All right, so we're going to first look at the Arrhenius definition of acids and bases. So as you can see, I wrote some up here: HCl, HNO3, HClO4, H2SO4. These are covalent compounds. So the hydrogen is covalently bonded, that hydrogen out in front is covalently bonded to the next element in the formula. And usually polar covalent substances, which these are, will dissolve because they have that partial negative, partial positive charge, but they don't usually dissociate into the ions. Okay, that's typical of polar covalent compounds. But acids are kind of unique. Acids do dissociate. So I have an HCl, it will break up into H plus and Cl minus when put in water. So they kind of act like polar molecules, and they act like ionic molecules when you put them in water. So they will dissociate and dissolve. Arrhenius says that an acid, when you dissolve it in water, will create an H plus concentration. And a base, when dissolved in water, will produce hydroxide or OH minus in the water. Okay, that's a great definition for if I'm just taking the acid or base and putting it in water, but what if I want to do a chemical reaction? So Bronsted-Lowry came around and said, let's have a new definition. We call an H plus a proton. It's a positive one charge. And Bronsted and Lowry said that an acid is a proton donor. So here's the acid giving its H plus to the proton acceptor, which is then the base. So this H2O accepted the base. H3O plus is really the same thing as H plus in water, just so you're aware. But the idea is that the stronger the acid is, the weaker its conjugate base. So there's kind of a pairing, right? We have this acid, it donates its proton, it donates its H plus. What's left over? It is called the conjugate base, and it is a base. So if we have a really strong acid here, this is going to be a weak base as the conjugate. Same for strong base and conjugate acids. So this one, just a little practice with that. What is the conjugate base for HCO3 with a -1 charge? So this is going to be our acid because I'm asking for the conjugate base. So if the acid gives up this H plus, that means it's gone, it donates it, so we're left with the CO3, and now it has another negative charge, so a -2 overall. Okay, now I want the conjugate acid, which means this is the base for HPO4 2-. So conjugate acid, a base is going to accept an H plus, so we get another H plus out in front, we get PO4, and we just have 1- because it gained that proton, that +1 charge. And then one other definition, I think we'll actually look at this more at the end of the unit, is the Lewis definition for acids and bases. So sometimes we don't have a base with an OH-, for example, or an acid with this long-standing H+. So Lewis looked at acids as electron pair acceptors and bases as electron pair donors. So we're focusing on lonely pairs here. So if you look, this ammonium has a lone pair, and so this lone pair is going to be donated to the H plus in the form of a bond, and we make this bond here. Again, we're going to focus more on Lewis at the end of the unit, so don't stress too much about it right now. All right, now I want to be able to look at a formula and know how strong the acid is. One note, pH does not determine the strength of the acid. So our instinct is usually like, oh, pH, that's a really strong acid. But for us, for acids and bases, a strong acid is one that dissociates a lot. Right? So we have our HCl, it can split into H plus and Cl minus. A strong acid is one that will split 100% of the time, or very close to 100% of the time. So just to clarify, the easier this H breaks off, the stronger the acid is. So let's first look at binary acids. If I just want to compare an H bonded to a single element, right? So that H is bonded to a single element. As we move down a group on the periodic table, acid, base, and strength increases. Excuse me, acid strength increases. Why? As I go down, we add more energy levels, so our atom is getting bigger and bigger, right? More rings you could visualize on that element. And so that means if I'm getting bigger, I'm less attracted to the H+, which means it falls off easier, which is a stronger acid. So iodine is a much bigger element. That H pops off way easier on HI than it does on HF. So HI is much stronger. We already kind of talked about the conjugate base, so these are the leftover pieces after that H is donated. It decreases, the base strength decreases moving down. Why? Because this guy, as we have the anions getting bigger and bigger, that allows it to attract and accept the H+ ion. And it's kind of just, again, that opposite. The stronger the acid, the weaker the base. All right, an oxo acid is we have this H directly bonded to an oxygen, and then we have another element pulling on the oxygen on the other side. So the acid is going to become stronger as the electronegativity of that bonded atom increases. So chlorine is much more electronegative. Okay, what that means is it's pulling the electron density towards itself, which removes the electron density from this HO bond, which allows the H to pop off easy. The stronger the acid, the easier it is for the H to pop off. So the more electronegative this bond is between oxygen and the other element, the easier H will pop off. Another option is we could have an oxo acid, but the element, that Y element, that other central element, could have some additional oxygens. So if I have more electronegative oxygen, so this chlorine is pulling lots of electrons towards these chlorine-oxygen bonds, so the more oxygens on that central atom, the stronger the acid, because there's less electron density between the oxygen and the hydrogen. It's being hogged on this side of the molecule, so the H pops off easier. And remember, H popping off easier, stronger acid. So here are some different scales. We have one of these like on the chart in our room, but just different acids and their relative strengths, their base strengths. So we'll be using these sometimes throughout class. Here's another one. Again, just kind of paying attention to the different strengths of acids. And another one in case 2 was not enough. All right, we're going to look at the autoionization of water, which sounds really scary, but I promise it's not. I'll show you. So the autoionization of water is that liquid water is at an equilibrium, so we have our back and forth arrows here, between the H+ ion, the OH- ion, and the liquid water. So it's constantly breaking down into the ions and then reforming water. We could write a K expression for this, products divided by reactants, but only aqueous, no liquids in our KW, or our K expression. So H+ times OH-, and we have a value for that. We call it KW, not KSP, not KC. We call it KW to represent this specific reaction of water breaking into its ions, and it has a value of 1 times 10 to the negative 14th. So pretty small, right? This negative 14th, right? We're clearly less than 1. If we're less than 1, that means the reactants are favored. So again, mostly when I have liquid water, it's liquid water, but we do have a small enough amount that we should care of H+ and OH-. Just another thing you might see is when an H+ is added to liquid water, it forms what's called the hydronium ion, which is the same thing as H+. So when we write reactions of putting an acid in water, I could put water in the equation, and the H+ is donated and forms H3O+. But typically what we do is we will leave out the H2O and just show that the H is popping off, forming an H+. Again, it does the same exact thing as the hydronium ion. So when we do reactions, I'll show you kind of what I'm talking about in class. Temperature impacts pH and KW. You don't need to memorize this. All you need to know is that temperature impacts K, which we learned in Le Chatelier's principle. So temperature will impact your K value, which also means it will impact your pH. All right, let's do some calculations for strong acids and strong base, finding pH and pOH. So there's 2 different scales we use. We have a pH scale and a pOH scale. I'm going to focus mostly on the pH scale because that's what people are used to hearing, but just know the pOH scale exists and we'll be using it sometimes. But here's what it means. If I have something that's more acidic, okay, that means there's more H+ ions and our pH is going to be closer to 0. If we're more basic, we have more OH minus, and our pH is going to be closer to 14. Okay, pH does not determine if something is an acid or base. Okay, so it does not determine if it's an acid or a base. pH is a measurement of acid-base concentration. So it's like a different way of stating molarity or concentration. So pH is a measurement of acid-base concentration. Too often we see a pH and we're like, oh, it's an acid, or we see a POH and we can use that to identify. Like, that's not the point. It's not to identify if something's an acid or a base. That's what the definitions are for, right? Arrhenius, Bronsted, Lowry, those types of things. pH is a measurement of concentration. So let's talk about H plus and OH minus. To find the pH, we are going to take the negative log of the molarity of H plus. To go the other direction, if I want H plus and I'm given the pH, I'm going to take 10 to the negative pH. Same works for OH. Negative log of the concentration of OH will be POH, and 10 to the negative POH will give me the concentration of hydroxide. So if, just kind of some general ideas, if I have a concentration of H plus of 1 times 10 to the 0, and I take the negative log of that concentration, I get a pH of 0. So these concentrations we could plug in, and that will allow us then to find the pH values. If I'm given pH, 10 to the negative 14 will give me the molarity for my H plus, and the same concept works for the hydroxide. Okay, and then I just added, yours has, it probably says acids, neutral, bases. Again, that's kind of the misconception, and I just want to make sure I'm using those words correctly. So, like, yes, typically a very low pH means there are a lot of H plus ions, which is the definition of an acid, right? There's a H plus ions breaking off. If we have a high pH like 14, we have a basic pH, that usually means that we have a lot of hydroxide ions floating around. But remember, the pH and the POH scales measure concentration. So I think it's better to say that if we have 7 or lower, it's an acidic pH. 7 or higher is a basic pH, and 7 is our neutral pH. All right, so I can put this kind of like in a map or a square because of this autoionization of water, right? We know that Kw is equal to 1 times 10 to the negative 14th. So using that idea, I can go back and forth between pH and POH, and I can go back and forth between H plus and OH minus. So this square will be helpful. So say like I have an H plus, I want to get to pH, I can take the negative log of that molarity and get pH. Then if I take 14 minus the pH, I will get POH. If I want the OH minus, I take 10 to the negative POH, right? So you can follow this. And last but not least, the concentration of OH minus is equal to Kw, which is this guy right here, 1 times 10 to the negative 14th, divided by H plus, because I know Kw equals H times OH. So if I rearrange that nice equation, I get this guy right here. Okay, we can go the other direction. Again, this just allows us to convert. It doesn't matter what direction you go. I always try to find the shortest path. All right, so I would like you to try these problems. I can maybe do the first one for us. So I have, don't worry about these if I don't give you anything, okay? These are for later if we know it's HCl, there's H plus, right? But up here, let's do this first one. So using the pH square, if I want to find pH, I know that pH is equal to the negative log of H plus. So if I take the negative log of 0.048, I get 1.32. I know POH is 14 minus the pH, so 14 minus 1.32 gives me 12.68. And the concentration of OH, I'm going to use my POH, so 10 to the negative POH will give me this guy, and I get 2.0 times 10 to the negative 13th molar. Again, could I have gone this way, and then to this one, and then to this one? Sure. Doesn't matter what order you go, you pick the path that makes the most sense to you using that pH square. So pause the video and try these next problems. Here are the answers for you to check yourself. Hopefully you got them all right. I'll see you in class.